Thanks, Patrick. G'day. It's great to be here. My name is Brendan. And in this talk, I'm going to show you how you can analyze container performance. There's some good and some bad news. The good news is that containers as operating system virtualization merely partition up resources, and Unix as a time-sharing system has managed switching between resources and partitioning for many years. The analysis of containers really isn't hugely different. I can look at who's consuming what, how they contend with each other. So that's the good news. In theory, containers don't actually make a big difference with performance analysis as it is OS virtualization. The bad news is that, well, the current implementation does add extra layers. Sometimes you're using overlay file system. There are some things that haven't been implemented yet. cgroups are still being rolled out. And so there are a lot of details that require attention and require knowledge. Some of the operating system analysis tools, they're not container aware yet. So when I run them from within a container, I'm looking at the host resources and not the container resources. So container analysis should be easy. It's something that, in a way, we've done forever with time-sharing systems, looking at how processes, different applications on the same machine contend for resources. Now it's different containers and their processes contending for resources. But some of the more complicated things with it are that they are not everything has been done that we need to be done in containers yet. The takeaways for my talk will be to identify bottlenecks in the host and the container using system metrics, to be able to understand what the applications are doing in containers, especially using CPU flame graphs, and then to be able to get into the kernel using tracing tools and how all of that works. Again, like I said, this should actually be pretty easy. Everything should just work. But the current implementation of containers, when I begin to use these tools, when I begin to use my profiling tools to look at my application code, things don't work because they're not namespace aware yet. When I begin to use tracing tools to dig into the kernel activity, things don't work yet. It's better now than it has been when I started getting into Linux seriously a few years ago, and it's going to get better still. I'm going to focus on how containers work in a modern version of Linux. So I will use Linux 4.9 for a lot of the screenshots. Hands up if you're on Linux 4.9 or above. So we have like maybe a quarter of the people. It's a really good vintage. You get a lot of the BCC, BPF things that are exciting. So please upgrade. I work at Netflix. At Netflix, we have Linux on the cloud, and that's running Ubuntu, the Amazon EC2 cloud. We also have FreeBSD for our CDN. And so when you log into Netflix and you authenticate and browse titles, you're coming from Linux. And when you hit play, you're coming from FreeBSD. As background, before I get into containers in a lot of detail, I'll briefly explain Titus, the Titus project at Netflix. Titus is a runtime platform that we've created to schedule containers. And so it manages service and batch job management and container execution. In particular, we've coded Titus so that it works with the EC2 APIs and does the things one would expect with Amazon. So dealing with security groups and VPC and EC2 metadata. There is a blog post at Netflix that goes through Titus in detail. Our current Titus scale, we have launched over 1 million containers in 1 week, just to put a high watermark out there. There's many instances, so they can be very large instances like M416 XLs, and we have thousands of instances for our Titus cluster. And it's used for ad hoc reporting, media encoding, stream processing. The Netflix cloud, it's a distributed system environment, and there are, depending on how you count it, you may say there are about 30 major microservices, and there's many, 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 many minor microservices. Titus is currently supporting several different applications. So all of Netflix is not on containers yet, but some important applications are definitely on containers. So it would be a bit hard for me to pick a percentage of how much of Netflix is containerized, but it may be something like 20 to 25%. But I might be wrong, so it depends how you count things. What we care about for container performance at Netflix is being able to scale and balance workloads. Fortunately, EC2 already gives us the ability to scale up as we need. So balancing new containers and new work around our existing cluster is a little bit different than, say, having a data center where we have a fixed capacity. We generally keep the Titus cluster fairly fixed, but we always have the ability to extend it and grow it. And so EC2 already gives us an environment where performance scalability is, in many ways, a mostly solved problem. The actual needs we have for container performance analysis include getting application analysis to work. Like I said, this should work, but when you go and run the profilers within the containers, the profiler is not container aware, things explode, they core dump, and we need to get them to work. Host tuning. How are things different now that we're on containers? How do we set up the file system? Is overlay AFS the right thing to use? And the same for networking. Do we use bridged networking with Docker and the other options available? Evaluating them. What are the sysctls we're going to use? Container analysis and tuning, and capacity planning, monitoring our Titus cluster and making sure that we have enough capacity. So those are the main things that we're looking out for at Netflix. Some container background. Now, a lot of you, I'll go through this very quick because I'm sure a lot of you know this very well. And also there was a talk this morning by Michael Jennings who went into the unprivileged namespace, the user namespace, and also did an introduction into namespaces. So namespaces are an important part of how containers work, and that is where we can restrict visibility, restrict what you see for processes that are running. So I've got some processes, and for the process ID namespace, they cannot see other processes. They may be process ID 1 in their own separate namespace. That's not going to clash with process ID 1 in the host. And the same is true for the IPC namespace, the mount namespace, net, user, and UTS. These are all ways to restrict the resources that are available on the host to a group that we can associate with the container. The other part is control groups. Control groups restrict usage. And at the moment, there's many. And a lot of these have been around for a while as part of cgroups version 1, but they are getting updated. And there's also cgroups version 2, which is partially rolled out into the Linux kernel at the moment. So this is definitely a moving target. But with cgroups, we can do things like allocate CPU to a container, not just in a fixed way, like give 1.5 CPUs to a container, but maybe in some shape, which is why I was drawing trapezoids in my diagram. Maybe I want to set some minimum and upper bounds to CPU usage for a container and for other things as well. So Linux containers, they're the combination of namespaces and cgroups, and that gives us a container. Cgroup version 1 that I mentioned that has the CPU and CPU accounting cgroup, that lets us do things like caps. So I can say this container can only consume 1.5 CPUs. When I say this container, it's really this cgroup, and that cgroup is associated with the container. I can do shares, which is a different way to allocate CPU resources. Memory has its own limits that I can control as well. So limits, kernel memory limits. I can disable for the cgroup. Block I/O has weights, IOPS and throughput caps per storage device as well. So these can all be used to balance resources so that we don't have noisy neighbor problems and containers can be isolated in a sensible way. We often want containers to be able to what the industry would call bursting, use more capacity if it's idle, and then shrink down to some minimum guaranteed if that capacity is not idle. I mentioned some of the Docker commands that are supported. We're currently using Docker for the Titus cluster. CPU shares are interesting in that they're pretty easy, but when you first encounter them, they may not seem so easy. The notion of CPU shares has been around in computing for decades, and it works like this. If my container had 10 shares, and I'd allocated 100 shares on the system, but only 20 shares were busy, then I can do a calculation and say my 10 shares divided by the 20 busy shares on the system is 50%, that means I can get 50% of the CPU capacity. And it's this formula that allows us to do bursting if that's something you want to configure. If I'm the only busy container on the system and I have 10 shares, the number 10 doesn't mean anything, it's arbitrary. I just dish them out. If I'm the only busy container on the system and I have 1 share or 10 shares, I can consume 100% of the system's capacity. If everyone's busy at the same time, and that's a different thing to consider, you could call it the container's minimum guaranteed CPU limit, and that's where you can divide your share by the total allocated shares. That's worst case, if everyone wants to use those shares at the same time. So it's nice because it gives us this sliding scale of worst case to best case. It means containers can burst and consume extra headroom. But it's also not nice in that a lot of performance monitoring tools are based on CPU utilization. And the notion that when you get close to 100% CPU utilization, you'll have run queue latency. I know there's going to be application issues. What's utilization on a system like this? So doing a calculation of percent utilization when your CPU capacity is actually relative to how many other people are busy at the same time. I could have a case where my application is consuming half the CPUs on the system because I have 10 shares and 20 are busy. And then another container begins to be busy. And my available CPU capacity goes down from 50% to 30% of the system. Now, it looks like there's a performance problem, but just in terms of CPU utilization as a metric, that's the only thing you're looking at in your monitoring graph. CPU utilization went down, so I guess I didn't need so much CPU. Not the case at all. It's because another neighbor has begun to consume the CPU. As a performance engineer, I have to explain this over and over and over when people are running into this issue. And the solution, I mean, you're welcome to help with solutions to this. One of them is you have to include share information with CPU utilization, so you understand whether you're bursting or if you're not. An analogy that gets used is when you fly in a plane, if there are no seats next to you, you get happy because you can lie down and go to sleep. I do these flights to Australia, they take a long time. But other people can come in and take those seats, and then you might be less happy. It's like, wait a minute, this was really comfortable, but now it's not. And that's because they're now consuming that extra headroom. cgroup version 2 is in the works, and it supports nested groups. It has a better organization and consistency, and a lot of it's already merged. And so do check that out because that's going to change things. Another key part of the basics for containers is we need to be aware of the OS configuration. So file systems themselves, perhaps ideally there would be nothing extra for us to turn on or no extra layers, as ext4 would be able to simply support multiple containers and be container aware. But at the moment, we quite often need to set up AUFS or overlay FS on top of the backing file system, ext4, to support containers. And those things come with performance overheads. So as a performance engineer, now you're doing evaluations. What's the different ways I can configure file systems to support containers and what's best? Docker actually came up with a good in-practice page where they go through the different storage drivers and the pros and cons. Networking, it's the same deal. Maybe in the future, the TCP/IP stack will seamlessly be container aware and not require any extra things to be extra layers to be turned on. But at the moment, we often have to set up bridge or host or overlay networks, and they have performance tags. They can have significant performance tags. So understanding the OS configuration, and in the talk earlier today, it was said by Michael, look at your Docker file and see how many lines there are in there. And you need to understand that. That can be layers and overhead. Analysis strategy for containers. It's important to be aware of, and I already mentioned, that there's namespaces and cgroups, but there's also two perspectives. When I'm analyzing a container system, am I analyzing it from the host or from within the container? And also there's only one kernel, which has its benefits to understand. I don't have to understand the interaction between a host kernel and guest kernels like I may do for KVM. And then you can apply a lot of existing methodologies to it, like the use method, workload characterization, checklists. Just to give you an example of one of them, the use method is something I came up with a while ago, and that's where you draw a functional diagram of the system, and for every resource you check utilization, saturation, and errors. And so for CPUs, utilization can be time busy, saturation can be run queue length or latency, errors may not make sense, but maybe ECC errors for CPUs. It's just a methodology to pose questions you want answered, rather than starting with what the metrics the system gives you, which can lead to blind spots. You can apply this to hardware resources and software resources and cgroups and the soft limits. So I can treat the CPU cap as a resource. What would the utilization of a hard CPU cap be? It would simply be how much you're using it. What would saturation be for a hard CPU cap? Well, there's actually a kernel counter for that. When you hit it, the kernel increments a counter that you are throttled by the cap. So that's good. Would there be an error metric that's important for a CPU cap? I haven't found one, but there could be. Maybe the cap is failing for some reason and it's failing to be configured. Something even harder would be, let's do the use method and apply it not to the fixed cap, but to CPU shares. How would I determine utilization of my share allocation? What would I calculate as saturation of my share allocation? Now you start to really think, because things get complicated. And that's the point of the methodologies, to help you think and work your way through performance. I don't have excellent answers to those, so work in progress. To go through actually how to do the analysis, so host tools to start with. Analyzing the host, if you have access to it, you may be in an environment where you only have access to the guest containers. But if you have access to the host, challenges to be aware of is all the process IDs you're looking at will be different if it's configured inside the guest container. So I may be looking at, process ID 181 is consuming too much CPU and it's consuming too much resources. And you have a look in the container and you can't find it. Or you talk to the developers and they can't find it either. And that's because of the namespace. It's just something to be aware of, that it has a different area code, it's got a different phone number. Symbol files aren't where tools expect them. So if I use a lot of performance profiling, debugging tools, it will try and read the binary itself to get symbols. It might try and read a supplemental symbol file from /temp. And for containers, if I'm running the tool from the host, it's looking in the host locations, but they're actually in a different mount namespace, so I can't find them. The kernel also currently doesn't have a container ID, although it has been proposed on LKML, and it was discussed recently again. But that can make it difficult as well. When you're using kernel analysis tools and you're trying to associate all this resource usage or these event usage, which Docker container is doing that? The Docker ID is not in the kernel. It's not the output of your tracing tools. So there's extra hops one needs to do of what's the container ID or the namespace ID. OK, now which Docker container uses the namespace or container ID to make the mapping? To look at host, the physical resources on a host, this is from the host perspective. This is basic performance analysis, so this is really a refresh I'll go through quickly. And I'll mention the CLI tools. It will solve many issues, even though this sounds like it's traditional performance engineering and nothing special for containers. But that's also kind of the point. Many performance issues I see in practice are not container specific. Many performance issues I see in practice are standard system performance issues. Disks are slow, networking is slow, we're out of CPU capacity. And so just because you have a container system doesn't mean you have a container problem. You do need to go back and just look at the standard host and exonerate that or find that that's to blame first. Here's one of my latest Linux performance tools diagrams, just to show the mapping of where these tools can be applied to different areas. And if that seems like too much, I did do the top 10 tools I would run on an instance to do host performance analysis in 60 seconds. I shared this on the Netflix tech blog. And so anytime there is a container performance issue, if you have access to the host, please start just by running these. These use the kernel bean counter, so they're basically free to instrument and measure. And things like uptime, demessage, because the kernel often tells you when it's sad and why. vmstat, mpstat, just to check the basics for resources. The use method itself I have iterated in the past for different hardware resources and some software resources, and so I've published them online. And so you can do that iteration yourself. Here I've got examples for the command line tools like mpstat and vmstat and perf. You may want to do the use method for your own internal monitoring GUI. So a lot of companies, at Netflix we have over 100,000 instances now in the cloud. SSHing onto an instance is a last resort. That's something we try and avoid. So we try to do everything from GUIs. So even though I've drawn the commands here, that's one way to do it, but you may want to come up with the GUI way to approach this. At Netflix, we have customizable dashboards. And so we can create a custom dashboard that steps through CPU utilization based on the utilization counters that our Atlas monitoring tool gathers cloud-wide, and saturation and so on. And maybe that's something you can do the same, creating your own custom dashboard to look at this. And then event tracing. If you can log into a system, you can analyze resource usage event by event. So here's my IOSnoop tool. That one's using ftrace, and so I'm printing out disk events one by one. Imagine how many times you've run TCP dump to who's run TCP dump to debug a network problem? Like everyone. Who's run an IO tracing tool to debug a disk problem? Oh, that's pretty good. All right. Hands up if it was one of my tools, like IOSnoop or BioSnoop. Is he using block trace or something else?
Desktop?
I said a tracing tool, like event by event. You use desktop. So it's great if you're using it. So same mentality. TCP dump can give you the events by events, which can be helpful. And then for disk resources, same deal, events by events. And things like desktop probably work, actually. Probably run that and solve the problem. You don't need to go to event by event. Up at the file system, actually, I like my tools like CFS slower. There's also ext4 slower and XFS slower as well. And that's where I'm tracing latency at the file system before we get down to the disk subsystem. Much, much better because it is a better indicator of pain for the application than looking at the disks rattling, because this is actually what the application blocks on, is file system I/O. And so there's some example from our production Titus system. And I can summarize that as histograms as well. So Btrfs dist, so it's looking at the distribution. I've got a multimodal latency. So yes, please use all those tools for the container host. Now, if you have access to the host, these are the tools that look at containers from the host. I was just looking at resources. I think it's worth just getting the mental picture of what's configured. And so I came up with a shell script called Docker PSNS. So this is basically a proof of concept for Docker PS ---- namespaces. And that became tickets for both Docker and Kubernetes. So hopefully that's now integrated. So there's a way you can do this. But the idea was I want to list the containers on my host, and then list the cgroup IDs. And here I've highlighted in red when a cgroup is shared with the host. So quickly I can see the cgroup itself, cgroup, and the user cgroup, they're both shared with the host, but everything else has their own separate cgroups. So just a quick, and also I print the process ID as seen from the host of the first process in the container. So hopefully that's now just Docker PS ---- namespaces or something similar. There is systemd cgtop, another useful host-based tools for looking at the containers. So that lists out control groups and then gives you a high-level total CPU consumed and memory. If you're using Docker, there's Docker stats, which I think they really should have called Docker top. But Docker stats gives you a top-level refresh of which containers are consuming how much CPU, memory usage versus the limit, net I/O, and block I/O. If you run top on the host, you will see all the processes on the system, but no container IDs. Now, We could fix that and add a container ID column to top, but it's a little bit tricky because the kernel doesn't have a container ID yet, although that could change. What has a container ID? Docker has a container ID, Kubernetes has a container ID, and various other ones have a container ID. So now would we need to make top Docker aware? That's a bit strange, because top just reads the proc statistics. So you can see why this is a little bit tricky, and we haven't really done it yet. It should be done. If a container ID finally lands in Linux, that'd be great. Then we'd add a container ID column to top. Optional. Or htop, because htop lets you select the columns. At the moment, with htop, you can select the C group, but it's, with Docker, it's getting truncated, and I can't see the full thing, and so there's problems with that. Also from the host, how do I go from the host process ID to the container process ID? No, this is just the host process ID to the container. So I know that this process, I just saw it in top, process ID 28321 is consuming a lot of CPU. I'm running this on the host. Who does that belong to? I can grab that in sysfs cgroup, and then for the CPU cgroup, docker star tasks. And it says this UUID is that process ID. This is dependent on how Docker is creating and using those cgroups, so that can actually change. And it's only working for that cgroup version 1 layout as well. At least there's a way to do it. I can also look inside proc, and I can pull out the namespace IDs and try and figure it out from there. And so there's namespace IDs, and also there's a cgroup file in proc. So here's some different ways I can start with a process ID and start to figure out what container it belongs to. Another way is I can use nsenter. Nsenter is the magic command which lets me assume a namespace and then run commands from that namespace. So I can say nsenter, there's my process ID, do the UTS namespace, and run the hostname command. And it says, I am Titus dash whatever worker. And so there's various other tricks I've got in the slides, which I'll share online. Nsenter, process ID for the hostname, the container netstat. I can get the container file system usage by running df-h in the mount and process namespace. I can also do a container top just by running top in the process namespace. I should really make these bash aliases so they're easier to type or something. So there's an example of nsenter. There's my target process ID, mount space, process ID namespace run top. Now I'm running top inside the container. And I can see that process ID 28321 is actually probably this hot process here, 301 Java. I can confirm it because it is actually in proc. It's in proc PID status. There is an ns PID line which maps the host process ID to the guest process ID. This is something that a lot of observability tools are going to need to scrape so that they can figure out that sort of mapping. Now, performance profiling. So I'm still in the host and I want to look at the containers. If I run, say, perf record, and of course at Netflix we care about performance profiling all the time, and I try and run perf script, then things blow up. And I sort of mentioned this earlier. It's because I'm running perf script in the host. It's looking for symbol files and the auxiliary map file in the host mount namespace and not looking for it in the containers mount namespace. That's the problem. Alice Goldfuss did do some excellent work and figured out how to copy it all around so that you can run perf in the host and then copy the needed files into the host namespace and actually succeed in doing flame graphs. And I actually copied that work and got that working at Netflix. So at Netflix now, if you do a flame graph on our Titus container systems, I do this copying tricks of dragging in the map files. This will get easier post Linux 4.14, which is not even released yet. We're up to, what, RC7. Linux 4.14, Krista Johansson has done a patch set for making perf namespace aware. So perf will look into the namespaces and say, oh, this process is in a different namespace, so maybe I should look for the auxiliary map files in that namespace. It's like, yes, of course. But this is an example of these tools haven't been all updated to be container aware yet. And as a performance engineer, this is our current problem, is walking on the minefield of what works and what doesn't work, coming up with workarounds, trying to get the kernel fixed. In the future, this will be pain long forgotten in the past, because we'll have fixed everything. But we're still in the process of fixing things. So CPU flame graphs. Who's used flame graphs? Flame graphs, hooray, I've got like 70% of people. So flame graphs, obviously a quick way to understand a complicated profile. And with containers, if you run a flame graph on the host, you can see all containers all at once, which might be exciting. I'm actually starting to use I should add it to this slide. I'm starting to use the --c group flag for perf record a lot so that I can just record one container and then from the host and then do a flame graph just for one container. That's an example of a broken flame graph because I didn't fix everything. It's missing the stacks for Java because I'm not running it with preserved frame pointer. And actually, it has the kernel TCP/IP stack, which is useful for understanding C group overheads and whatnot. C groups are another resource I can poke around with from the host to understand containers. So there's my CPU-C group. It's got, say, usage, there's metrics, there's a CPU.stat. That one's interesting because it has throttle time for the cap, the CPU cap, if that's configured. That will then tell me how many nanoseconds it's been throttled, so you know if you've hit that. That should be included in performance monitoring GUIs. Speaking of GUIs, Netflix Atlas is the environment-wide GUI we use at Netflix, and we're fetching C group metrics via Intel Snap at the moment so that we have access to them. Netflix Vector is another open source GUI we've developed. This one is for instances only, and we have a whole heap of container things, so we can do per container, CPU utilization, and memory and disk. And last quarter, I added container-aware flame graphs so that on Netflix Titus, you can click on one container and just get a flame graph for that one container. I'm using the perf record --c group flag. And I mentioned Intel Snap. That's a collecting agent that has a Docker plugin for C group stats. There's also a collect_d plugin if you're using that so that we can get the information. As an example that things do get a bit complicated with containers, I have let's play a game. Let's see if we can figure out whether this is host or container. I'll just do one of these, but there's more in the slides. So the container user claims they have a CPU performance issue. The container has a CPU cap and CPU shares. They're both there. There's idle CPU on the host. Other tenants are consuming CPU resources. Our throttle time metric is increasing. Our non-voluntary context switches is increasing. It's another telltale sign. Our container CPU usage equals its cap. So our CPU usage is, say, at 200%, and the cap is 200%. That sounds like we're hitting the cap, but we may not be. We may be throttled because of shares. It may just coincident, I just got to the cap, but shares is holding us back. Hands up if you think this is throttled by the cap, CPU cap. No one. Hands up if you think it's throttled by the CPU shares. Okay, 3 people. What about it's just throttled by the system itself? The system's out of CPU resources. Just normal, okay, a couple of people. What about not throttled? The container is not throttled. Yeah, a few people. I wrote these slides a while ago, and I was refreshing them just before I gave the talk. And it's like, wow, this is actually kind of tricky. Even for myself, this is hard to figure out. There's a lot of things going on. And so you can play that game in my slides, but I came up with a way to figure this out where I enumerated the possible outcomes. And then I worked backwards to what metrics do I need to diagnose one of these outcomes. So we're either physical CPU throttled, and that's where, like, you're just out of CPUs. It doesn't matter what the software configuration is. You're just out of CPUs. You're cap throttled, which is the hard cap. You're share throttled. And you can only really be share throttled if you're physical CPU throttled. Because if you're not physical CPU throttled, then you can still burst. Or you're not throttled. So I came up with this diagram, which helps a lot. I'm glad I did that. If throttle time is increasing, you're cap throttled. Let's take that off the operating table straight away. It's nice and simple. In that first example, that's the metric that tells us if the CPU cap has been hit. that was being hit, we know we're cap throttled, we're done. If not, if non-voluntary and context switches are not increasing for that process or container, well, it means we're not getting kicked off CPU. And if we're not getting kicked off CPU, we're probably not getting throttled. So that would tend to put us into the not throttled basket, unless you have some other theory and you need to dig into the kernel and debug that. But I'd be expecting that to be not throttled. If you are getting kicked off CPU, so you've got non-voluntary or involuntary context switches, then do you have idle CPU? If you have idle CPU, but you're getting kicked off CPU, something strange is happening, like interrupts. So that needs further digging. If you don't have idle CPU, you're getting kicked off CPU. You're not getting throttle time. That's when it's other tenants idle or not. And if other tenants are not idle, then you're going to have share contention. And if they are, you're the only tenant on the system, then your physical CPU throttled. Phew, that's pretty complicated, but can be figured out. If you want to, I only did this for CPUs. If you want to do this exercise for disks and networking and everything else, hopefully it's not as hard. Start with the final outcomes, because disks have the IOPS caps and the throughput caps. Start with each of the possible outcomes, and then try working backwards to come up with a differential diagnosis, so you can then go from the metrics you have to one of those possible outcomes. This should all be in a GUI. This should just be a wizard that tells me. In fact, it should just tell me the outcome. You are cap throttled. So that was host tools looking at the container. I'll go through guest tools. Guest analysis challenges. Some resource metrics are for the container and some are for the host. I mentioned this earlier, so it's a bit complicated from the guest. And guests may lack system capabilities to run profilers and tracers. CPUs, if I run my CPU commands, I can see the host CPU devices, but only the PID processors. So if I run uptime, my system has load, but if I run mpstat, I can see the load, but then if I run pidstat on top, I'm not consuming the load. So this seems wrong, and it's because the top two tools are showing me the host, and the bottom tool is showing me the container. This is running from within the container. In the future, we may make load averages container aware. So you run uptime, and you get a container load average. And there's already load average metrics for CPU groups and C groups. So it's very possible. But at the moment, that's how it is. For memory, you can see host's memory. So I've got 15 gigabytes. No, I've got 8 gigabytes free, but I can't seem to consume 2 gigabytes. I get killed. So that seems confusing. That's also confusing to some applications, too. I start Java, and Java may automatically pick a heap size and think, hey, I can just use 8 gigs. No, you can't. And then Java gets killed. And so sometimes with applications, the JVM in previous versions was not container aware. And so that needed to be configured. Disks, you can see the host's disk devices, but no one on my container is consuming the disks. Network, I can see the host's network interfaces. So I guess at this point you might feel we do have a lot of work ahead of us to make everything container aware, so it makes sense from within a container. One way to do that might be to create a metrics namespace. And this is just my idea. It may never happen, but a metrics namespace could have container versions of proc host stats, proc host disk stats, and so on, so that those tools like IOStat would just naturally work. CPU profiling from within in a container is difficult, since it requires perf event open syscall, and Docker currently block that. So that's running perf from within a container. We did figure workarounds for it, so we have been able to get it to run with Docker, run cap add sysadmin, and then you can create flame graphs. But the easier way we're actually doing it from Netflix is creating flame graphs from the host of the container. So Netflix Vector runs on the host, people connect to a website, and it gives them a per container flame graph. The last section I'll mention briefly is how does tracing work with containers. Nowadays, it's exciting as we have eBPF that gives the kernel these dynamic tracing capabilities. But in the past, these still exist. ftrace and perf events give us many more. I've created toolkits. So I created perf tools for ftrace, and I've been contributing to BCC. which uses eBPF. And if you're in the talk earlier today, Sasha Goldstein talked about BPF analysis of Java. Some things we might want to do with the traces. ftrace, I'm analyzing the overlay fs function calls. So I'm running func count on OVL star, well, star OVL star, and I can see all of the kernel function calls for overlay fs. Overlay fs isn't super fast, and maybe I want to drill into those functions and find out why. So this is a beginning of some analysis. I can run my kprobe tool. I can begin with a overlay fill merge and then print out details in the stack backtrace. So traditional tracing, that's just using ftrace, but we can use BPF as well. And BPF is great because it can do in-kernel aggregations and asynchronous copies of the data to user level, and that makes things much more efficient. And we've created many tools for BPF. This is just the BPF tools, and a lot of these were created by me and Sasha. So you can get into some multi-tools for kernel analysis, but also to the file systems, disks, TCP, scheduling, activity, and so on. And these should all work from the host just fine. From the container, however, they need resources, just like perf event did. So it's a work in progress to get them working from within a container. So you can do things like look at scheduler latency. So this is per process namespace histograms. So I can see how that was working. Oh, no, so this is the per PID namespace histogram. So there's one histogram for each container is how that will work. And you can also analyze, say if you're using Docker or Kubernetes or something else, you can analyze that as well using tracing tools. Docker is written in Go, and there's many different ways to analyze it. And you can also use BCC and BPF. And just as an example of that, here's func count of dockerd, and I'm looking at the Go calls using BPF, dynamic tracing. And there's 35,000 functions I can trace in Docker. I can pull out stack traces for Docker events as well if I really want to drill down deep. So there's lots we can do for tracing of the kernel and also the container runtime. In summary, this talk I went through identifying bottlenecks in the host and the container using system metrics, in the application code using CPU flame graphs, and deeper in the kernel. And I'll share these slides online and have a lot of references for drilling down deeper. Thank you very much.